Alright, hello everyone, and welcome to my channel. This is an educational channel. We take a look at great theories of everything, ancient and modern, and try to get into them deeply, let you see how they can be used in your life to improve your circumstances. And today is our 508th video that we've done on the reciprocal system of theory from Mr. Dewey B. Larson. And Mr. Larson lived in the 20th century. He was an engineer. Born in North Dakota, moved out to Portland where he did his work. And in 1959, he proposed his two fundamental postulates about how the universe operated. And then from those postulates, he derived a theoretical universe. What his universe would look like if his postulates were correct. And then compared his theoretical universe with the measured empirical universe of the modern scientists. And in many cases, Mr. Larson was able to almost recreate the scientific tables that had been laboriously constructed in the laboratory and observatory by these modern scientists. And Larson was able to recreate their results strictly from theory, right out of his head, with no budget. And so you must think that he must have been on to something. Not to say that his entire theory is correct or that everything is hunky-dory with the theory, but that there's certainly something there in my mind that deserves to be given a hearing at this point. Because I don't believe that Larson's theory has been given a proper hearing. It's kind of outside of the paradigm, the okay paradigms for scientific inquiry, which, basically include innovation, but not invention. You can kind of make waves along the margins, but when you call for any type of overhaul of things that scientists are invested in, you get no play whatsoever. And I believe that was the case for Larson all the way from the late 1950s until his death in 1990, and still today. I have actually never in my life, I'm studying this for almost 25 years. Not every single day that I study it, but I've never met another person face to face who's ever heard of him before. So, the theory's not out there. That's why I'm doing 500 plus videos on it. And we are looking, now if you want to get a more detailed or a detailed rundown of Larson's theory and how it works, his postulates, and their ramifications, you want to watch any of my first 474 videos. Excuse me. My first 474 videos on the subject. Where I go into it, at least for 15-20 minutes. In this video, I'm just going to be reading from chapter 20 of Larson's book that is called Basic Properties of Matter, where he, derives equations for many of the basic properties of matter, such as the melting point and the compressibility and the specific heat, and then he compares them with the scientific tables. Chapter 20 here is called Magnetic Quantities and Units. It's one of several chapters that Larson does here on magnetism. And it starts off like this. One of the major issues in the study of magnetism is the question as to the units in which magnetic quantities should be expressed and the relations between them. Since the first attempts to put its study on a quantitative basis, says J.C. Anderson, quote, magnetism has been bedeviled by difficulties with units, end quote. As theories and mathematical methods of dealing with magnetic phenomena have come and gone, there has been a corresponding fluctuation in opinion as to how to define the various magnetic quantities and what units should be used. Malcolm McCaig comments that, quote, with the possible exception of the 1940s, when the war gave us a respite, no decade has passed recently without some major change being made in the internationally agreed definitions of magnetic units. End quote. He predicts a continuation of these modifications. My reason for expecting further changes, he says, is because there are certain obvious practical inconveniences and philosophical contradictions in the SI system as it now stands, end quote. Actually, this difficulty with units is just another aspect of the dimensional confusion that exists in both electricity and magnetism. Now that we have established the general nature of magnetism and magnetic forces, our next objective will be to straighten out the dimensional relations and to identify a consistent set of units. The ability to reduce all physical quantities to space-time terms has given us the tool by which this task can be accomplished. As we have seen in the preceding pages, this identification of the space-time relations plays a major part in the clarification of the physical situation. It enables us to recognize the equivalence of apparently distinct phenomena, to detect errors and omissions in statements of physical relationships, and to fit each individual relation into the total physical picture. Furthermore, the verification process operates in both directions. The fact that all physical phenomena and relations can be expressed in terms of space and time not only enables identifying the correct relations, but is also an impressive confirmation of the validity of the basic postulate, which asserts that the physical universe is composed in its entirety of units of motion, an entity defined as a reciprocal relation between space and time. Okay, so that's basically Larson's first postulate right there. The conventional treatment of magnetic phenomena employs the units of the mechanical and electrical systems so far as they are appropriate, and also, in some specialized applications, utilizes the same quantities under different names. For example, inductance, symbol L, is the term applied to the quantity involved in the production of an electromotive force in a conductor by means of variations in the current. The mathematical expression is F equals negative L dl over dt, di over dt, change in current over time. In space-time terms, the inductance is then L equals T over S squared times T over S times T equals T to the third over S to the third. I'm just trying to see if that makes sense to me. I guess, okay. He did Larson tends to skip steps, especially when he's doing algebra. And I'm not very good at algebra. At least I try to do algebra, which is better than what most people do. But I think I understand where he's going with that. Okay, so these are the dimensions of mass. Inductance is therefore equivalent to inertia. Because of the dimensional confusion in the magnetic area, the inductance has often been regarded as being dimensionally equivalent to length, and the centimeter has been used as a unit, although the customary unit is now the Henry, which has the correct dimensions. The true nature of the quantity known as inductance is illustrated by a comparison of the inductive force equation with the general force equation F equals ma. F equals ma equals m times dv over dt, change in velocity over time, which is acceleration. So that becomes m mass times d squared s over dt squared. Force equals inductance times the change in current over time. And so then we get inductance times d squared q over dt squared. The equations are identical. As we have found, I, current, is a speed, and q, electric quantity, is space. It follows that m, mass, and L, inductance, are equivalent. The qualitative effects also lead to the same conclusion. Just as inertia resists any change in speed or velocity, inductance resists any change in the electric current. Recognition of the equivalence of inductance and inertia clarifies some hitherto obscure aspects of the energy picture. An equivalent mass, L, moving with a speed I, must have a kinetic energy, 1/2 Li squared, analogous to 1/2 mv squared. And we find experimentally that when a current I flowing through an inductance L is destroyed, an amount of energy, 1/2 Li squared, does make its appearance. The explanation on the basis of conventional theory is that the energy is, quote, stored in the electromagnetic field. But the identification of L with mass now shows that the expression 1/2 Li squared is identical with the familiar expression 1/2 mv squared, and that, like its mechanical analog, it represents kinetic energy. The inverse of inductance, t cubed over s cubed, is reluctance, s cubed over t cubed. The resistance of a magnetic circuit to the establishment of a magnetic flux in a magnetomotive force. As can be seen, this quantity has the dimensions of three-dimensional speed. In addition to the quantities that can be expressed in terms of the units of the other classes of phenomena, there are also some magnetic quantities that are peculiar to magnetism and therefore require different units. As brought out in the preceding chapter, these magnetic quantities and their units are analogous to the electric quantities and units defined in chapter 13, differing from them only by reason of the two-dimensional nature of magnetism, which results in the introduction of an additional t over s term into each quantity. The basic magnetic quantity, magnetic charge, is not recognized in current physical thought, but an equivalent quantity, magnetic flux, is used instead of charge, as well as in other applications where flux is the more appropriate term. The space-time dimensions of this quantity are the dimensions of electric charge, T over S, multiplied by the factor T over S that relates magnetism to electricity. T over S times T over S equals T squared over S squared. In the CGS system, magnetic flux is expressed in Maxwell's, a unit equivalent to 10 to the minus 8 volt seconds. The SI unit is the Weber, equivalent to the volt second. The justification for deriving the basic magnetic unit from an electric unit, the volt, can be seen when this derivation is expressed in space-time terms. T over S squared, force, times T equals T squared over S squared. The natural unit of magnetic flux is the product of the natural unit of electric potential, 9.31 times 10 to the 8th volts, and the natural unit of time, 1.52 times 10 to the minus 16 seconds, and amounts to 1.41 times 10 to the minus 7 volt seconds, or Webers. The natural units of other magnetic quantities can similarly be derived by a combination of previously evaluated natural units. Magnetic flux density, symbol B, is magnetic flux per unit area. The space-time dimensions are T squared over S squared times 1 over S squared equals T squared over S to the 4th. The units are the Gauss in the CGS or the Tesla in the SI. Magnetic potential, also called vector potential, like electric potential, is charge divided by distance, and therefore has the space-time dimensions of T squared over S squared times 1 over S equals T squared over S to the 3rd. The CGS unit is the Maxwell per centimeter, or Gilbert. The SI unit is the Weber per meter. Since conventional physical science has never established the nature of the relation between electric, magnetic, and mechanical quantities, and has not recognized that an electric potential is a force, the physical relations involving the potential have never been fully developed. Extension of this poorly understood potential concept to magnetic phenomena has then led to a very confused view of the relations of magnetic potential to force and to magnetic phenomena in general. As indicated above, the vector potential is the quantity corresponding to electric potential. The investigators working in this area also recognize when they call a magnetic scalar potential, which they define as B ds over m, change in space per matter. Not sure. Where S is space and m is a quantity with the dimensions T to the 3rd over S to the 4th that will be defined shortly, which is permeability. I don't know why that is an M. But anyway, the space-time dimensions of the scalar potential are thus T squared over S to the 4th times S divided by M equals S over T. The so-called scalar potential is therefore a speed, S over T, equivalent to an electric current, a conclusion that agrees with the units, amperes, in which this quantity is measured. W.J. Duffin comments that it is not easy to put a physical interpretation on magnetic scalar potential. The space-time dimensions of this quantity explain why. A potential, that is a force, equivalent to a speed, is a physical contradiction. The scalar potential is merely a mathematical construction without physical significance. As indicated earlier, the magnetic quantities thus far defined are derived from the quantities of the mechanical and electrical systems. The units derived from the electrical system are related to the corresponding units of that system by the dimensions T over S because of the two-dimensional nature of magnetism. Most of the other magnetic quantities in common use are similarly derived, and all quantities of this set are therefore dimensionally consistent with each other and with the mechanical and electrical quantities previously defined in this and the preceding volume. But there are some other magnetic quantities that have been derived empirically and are not consistent with the principal set of magnetic quantities or with the defined quantities in other fields. It is the existence of inconsistencies of this kind that has led to the conclusion of some physicists, expressed in a statement quoted in Chapter 3, that a consistent system of dimensions of physical quantities is impossible. Analysis of this problem indicates that the difficulty, as far as magnetism is concerned, is mainly due to incorrect treatment of the dimensions of permeability, symbol M, a quantity that enters into these and other magnetic relationships. The permeability of the great majority of substances is unity, or a close approximation thereto. The numerical results of magnetic measurements on these substances, therefore, give no indication of its existence. And there has been a tendency to overlook it, except where some collateral relation makes it clearer that there are missing dimensions. But its field of application is actually very wide. As our theoretical development indicates, that permeability is the magnetic equivalent of electrical resistance. It has the space-time dimensions of resistance, T squared over S to the third multiplied by the T over S factor that relates magnetism to electricity, the results being T to the third over S to the fourth. One of the empirical results that has contributed to the dimensional confusion is the experimental finding that magnetomotive force, MMF, or magnetomotance, is related to the current, I, by the expression MMF equals Ni, where N is the number of turns in a coil. Since N is dimensionless, this empirical relation indicates that the dimensions of magnetomotive force are the same as those of electric current. The SI unit of magnetomotive force has therefore been taken as the ampere. It was noted in Chapter 9 that the early investigators of electrical phenomena attached the same electromotive force to a quantity that they recognized as having the characteristics of a force, an identification that we now find to be correct, notwithstanding the denial of its validity by most present-day physicists. A somewhat similar situation exists in magnetism. The early investigators in this area identified a magnetic quantity as having the characteristics of a force and gave it the name magnetomotive force. The prevailing view that this quantity is dimensionally equivalent to electric current contradicts the conclusion of the pioneer investigators. But here, again, our finding is that the original conception of the nature of this quantity is correct, at least in a general sense. Magnetomotive force, we find, is the magnetic two-dimensional analog of the one-dimensional quantity known as force. It has the dimensions of force, T over S squared, multiplied by the factor T over S that relates electricity to magnetism. Dimensional consistency in magnetomotive force and related quantities can be attained by introducing the permeability in those places where it is applicable. Recognition of the broad field of applicability of this quantity has been slow in developing. As noted earlier, in most substances, the permeability has the same value as if no matter is present, the reference level of unity, generally called the permeability of free space. Because of the relatively small number of substances in which the permeability must be taken into account, the fact that the dimensions of this quantity enter into many magnetic relations was not apparent in most of the early magnetic experiments. However, a few empirical relations did indicate the existence of such a quantity. For example, one of the important relations developed in the early days of the investigation of magnetism is Ampere's law, which relates the intensity of the magnetic field to the current. The higher permeability of ferromagnetic materials had to be recognized in the statement of this relation. Permeability was originally defined as a dimensionless constant, the ratio between the permeability of the ferromagnetic substance and that of free space. But in order to make the mathematical expression of Ampere's law dimensionally consistent, some additional dimensions had to be included. The texts that define permeability as a ratio assign these dimensions to the numerical constant, an expedient which, as we pointed out earlier, is logically indefensible. The more recent trend is to assign the dimensions to the permeability where they belong. In the CGS system, those dimensions are arbitrary. The dimensions are ab-Henry per centimeter. The ab-Henry is a unit of inductance, T to the third over S to the third. And the dimensions of permeability on this basis are T to the third over S to the third times 1 over S equals T to the third over S to the fourth, which agrees with the previous determination. The SI units, Henry per meter and Newton per ampere squared, are likewise dimensionally correct. The unit farad per meter has been used, but this unit is dimensionless as capacitance, of which the farad is the unit, has the dimensions of space, which we were discussing in chapter 15 and argued that those units are wrong for the farad, and that the farad is really S to the third over T. Now, I don't know exactly how that goes into this equation, but using this unit is equivalent to the earlier practice of treating permeability as a dimensionless constant. McCaig is quite critical of the unit Henry per meter. He makes this comment. Most books now quote the units of M sub O as Henry per meter. Although this usage is now almost universal, it seems to me to be a howler. The Henry is a unit of self or mutual inductance, and it seems quite incongruous to me to associate a meter of free space with any number of Henrys. If one wishes to be silly, one can invent numerous absurdities of this kind, e.g., torque is measured in Newton meters or joule. The truth is that these two examples of what McCaig calls dimensional absurdities are quite different. His objection to coupling inductance with length is a purely subjective reaction, an opinion that they are incompatible quantities. Reduction of both quantities to space-time terms shows that his opinion is wrong. As indicated above, the quotient Henry per meter has the dimensions t cubed over s to the fourth with a definite physical meaning. On the other hand, if the dimensions of torque are so assigned that they are equivalent to the dimensions of energy, there is a physical contradiction, as a torque must operate through a distance to do work, that is, to expend energy. This situation will be given further consideration later in the present chapter. Returning now to the question as to the validity of the empirical relation MMF equals Ni. It is evident from the foregoing that the error in this equation is the failure to include the permeability, which has unit value under the conditions of the experiments, and therefore does not appear in the numerical results. When the permeability is inserted, the equation becomes MMF equals, that's some kind of Greek letter, Ni. Some Greek letter Ni. The space-time dimensions of which are t squared over s to the third equals t cubed over s to the fourth times s over t. The dimensions t squared over s to the third, which are assigned to magnetomotive force on this basis, are the appropriate dimensions for the magnetic analog of electric force, as they are the dimensions of force, t over s, multiplied by the dimensions of force, t over s squared, multiplied by t over s, the dimensional relation between electricity and magnetism. Okay, if you understood any of that, you probably did better than I did, but we will get back to this tomorrow and hopefully try to finish this chapter. So yeah, thanks for tuning in today.